So first, define the single cutoff rules. So the single cutoff rules are the ones that doesn't have an a. So a is minus infinity basically. So I basically only have the upper boundary. So it'd be something like this. So if u is above v, then we stop. So we stop on the right, and we continue on the left. So one way to think about this is if we move up and down this u function, then we can make the agent stop at any point. What is the requirement? So first we need u to be increasing. Second, we need that kind of single crossing condition, which means they intersect at only one point, and that point is where we want to implement our stopping threshold. So if we copy this several times, then we could move the first one first by shifting up and down u. But now there's a problem. When we do the second one, the first one gets shifted again as well, because when we change the second u, the v at the first time, so the valuation, I mean the continuation value in the first period would change. So that's not a good strategy. We should probably start from the back. So let's restart. So move the back first. So when I move the furthermost one, which is not that clear here, but when we move that one, all the previous v's will change. But that's okay, because then we can fix the second one. When I fix the second one, it doesn't change anything about the last one, but it changed everything before, so it's okay. So we can basically do things recursively like this. So we can calculate the prices. But the good thing, the lucky thing, is that we don't actually need to do that because there's an explicit formula for the prices. So from the algorithm that I described, we can have a recursive formula for the prices. But then to make that recursive form explicit, there is some formula here. So to repeat the conditions, we have our increasing u condition. The second line is basically the single crossing condition. Then anything here, important thing here is anything is possible. So there are some notation that you may not know. The I here represents impulse response function. The Z here is marginal incentives, which is basically the difference between utilities. And you have those transition kernels, which is just expectation over either the original process or some modified version of the process. These notations are not important, so I'm not going to go through them in detail. So what I described was if you only have one action, one possible action when you stop, but then the original question is that we have multiple actions. So we have Q here. So if we can choose different Qs, then the condition needs to be changed, but it's similar. So there are a lot of things that you don't know what they are. So the good rule is probably if any slides has a title that contains the words proposition, you are not going to read that slides because that slides is full of formulas that you don't understand. But in the next slide, I'm going to simplify those. So suppose we are doing the monopolist screening. Basically, a monopolist, as the principal, is selling a good. So at each time, an agent could stop and choose Q units. So the Q is can be continuous or discrete, doesn't matter. And the utility function is this particular utility function. And also we require our process to be the additive random walk. So in this case, we could simplify both of these conditions. So remember, we had two conditions. The first condition gets simplified to just Q is increasing X. So what this means is suppose my valuation is larger, then I should get more of this good, which is obvious. And the second one can be reduced to something like this. So to read this, it's the quantity that I'm going to get is larger than the expected quantity I'm going to get in the next period. So that's kind of obvious. No, it's not obvious that this implies single crossing, but it does.